This is the first part of the weekly review about the seminars that I attended. For new listeners, I am doing a sabbatical this semester, or maybe even the year. We'll see how long that goes. But I am at Stanford. I'm attending seminars, colloquia, lectures, all kinds of different events. There is a focus on robotics and AI, but there's also different types of events. So I'll discuss all of these things in several episodes. Usually I do them over the weekend and I discuss the past week. I'm going to start with three lectures I attended today. All three are in the realm of robotics, actually four lectures. So they're all a part of robotics, data processing, data analysis, data compression, really interesting stuff. I'm very privileged to be in this position. So I'm going to discuss Shirin Song. She talks about sort of what is really going on in robotics, what are the frontiers, what is interesting, so those sort of things. Her particular emphasis is on data collection for robotics. Priyanka Raina, she is actually, this is a really interesting situation where she talks about flexible hardware development. So it's a very different topic, but it's related to AI. Almost everything in computer science these days is related to AI. And the problem is that we have much faster developments of software and models. And she's trying to solve that problem with flexible hardware design. Next is Pulkit Agrawal, MIT researcher in robotics. He's talking about dextrous design for manipulation, hand tasks, things along those lines. Really interesting, very applicable to the humanoid robot. And lastly, I'm going to discuss Shirin Bidokati. I might be butchering her name, from UPenn. And she's talking about data compression. And really the big takeaway here is data compression and machine learning are very similar tasks. It's neural data compression, to be precise, where they try to learn from the distribution of the data, the geometry of the data. They try to learn how much they can compress and then decompress for signal processing. This is not even on podcast. It's November 17th, 2023. This is Crimdelco. Since the last update, we're up 17%. The market's up 3%. For the year, we're up 105.7%. The market's up 17.5%. We're outperforming by 88.2%. So Shirin Song, she's an associate professor at Stanford in robotics. I've discussed her before. She was part of BARS through 2023. She's also active, of course, at the at the Conference for Robot Learning, CORL 2023. I really don't like those acronyms that the community is using, but that's a different point. Anyway, so she gives a presentation about generalist robot learning. 4 big points: diffusion model for robot learning, data is key. She introduces the concept of robot complete data. She talks about using large language models for sort of a high level and low level activation for robots. So in a sense, she's introducing a concept that I've heard before, where large language models could be sort of the operating system of the future, because they can, you can prompt something and then activate something, and then so on and so forth. I'm going to discuss this in more detail. And then lastly, she talks about sort of an intuitive interface, which I thought was interesting. So for example, the self-driving car has an intuitive interface. It's the steering wheel and the brakes and the gas. It's very clear what the car has to do, and it's very standardized. Every car has the same type of technology, more or less. Robots don't have that, right? Robots, take the cell phone. We have a pretty standardized form factor, a camera. So these cameras, they get, they take pictures into some sort of, pixel voxel combination, whatever that is. And well, in the case of cameras, it's pixel. But what I'm trying to say here is that we have standardized technology, and we don't have that with robots. So she's sort of making that point. So let's talk about some of the details. So I think what's really interesting is, so the diffusion model for robot learning, Shirin talks about the possibility to use the idea of a diffusion model which we've seen in image generation for robot learning. So you have a similar problem, which is you have you wanna find a path from let's say in the case of diffusion, it's you have complete noise, and then you learn how to denoise the picture to create a dog. How do you do that? You do that by learning how to denoise the complete noise. And in terms of the trajectory planning of a robot, you could argue it's a similar problem where you have an action space which is fully noised, and now you denoise that action space and you find the path towards manipulation. So this is, I think, an interesting idea. I haven't read too much about it. I haven't read papers about it, but she's introducing this idea, and I think it's really interesting. The second thing she's talking about is how data is key. Her talk at CORL 2023 is about what I wish I had as a robot researcher, and it's about data. And the data is really not just about scale, it's also about the quality. She's talking about robot complete data, for example, which is absolutely important, which means that you need to have some sort of a data set that other people can use. This is something I've heard Sergey Levin talk about. Robotics needs standardized data, also not just having all kinds of data out there. You know, I'm grasping a banana and you're cleaning the floor. It needs to be in a way standardized, and this is a real problem that I don't see how can it be solved. But what she is offering as a solution is a standardized way to collect data. So she's having 2 students working on this. I have a feeling at Stanford everybody's trying to sort of become the next Fei-Fei Li. You know what she did with ImageNet. People now are now trying to do with robotics. Standardize something, create a large data set. I mean, it's a good idea. I have a feeling robotics is a little bit on the sort of incremental side. That's my concern, to be honest. So I'm not too convinced about all these approaches, but there's also this idea of all these incremental steps eventually leading to a more successful completion of the task. So last thing that I want to talk about in Shirin Song's presentation was the use of LLMs for high-level robot planning and also low-level planning. And this is a concept that I've heard the guys at theCUBE talk about, which is that large language models, sort of in the context of, let's say, Azure and Microsoft, could be used for really as an operating system. So in this sense, you have the large language models so the robot sees something, turns that into a textual prompt. You know, I'm in a room and the kitchen is over there, so go over there and get a pot and make me some pasta. And that gets prompted, and that prompt calls for functions such as, you know, walk, grasp, and then those functions call for lower level functions, actuator, you know, move the finger by this much, and so on and so forth. So this is the idea. So we have some sort of operating system driven by large language models. Next presentation by Pulkit Agrawal, MIT researcher in robotics. So very similar to Shirin's problems, actually, in terms of what he's trying to achieve: manipulation tasks, highly dexterous tasks. Pulkit was the chair of one of the workshops called Manipulation, the manipulation track at Coral 2023. So he's definitely in there as a big player in this field. So he fundamentally presents 2 ideas. One is reinforcement learning with human interaction. So this is similar to a talk I attended actually yesterday by Jens Kobel or Kobler. I might be butchering his name, but I'll discuss this in another episode. But it's about, okay, how can humans interact with a system? How can we have reinforcement learning with human help? And the idea here is that how do you incorporate human help? There's a paper that Agrawal et al. Published about this, and the key is, I'm quoting, in this work, we note that a promising sub-goal is one that satisfies two criteria. It is closer to the desired final goal than the current state and of the system. So it's closer to the goal. So the sub-goal is closer to the desired goal than some other action. And second, it is reachable from the current state. So that sub-goal is reachable. And the human could be helping by introducing the robot to the sub-goal. And this is really important because I was wondering, and I asked the question to Agrawal, and he didn't really understand my question. What happens if I introduce something that potentially might be not looking very good in the short term, but in the long run might be a better solution? And I think they're kind of excluding this by design, by saying, look, the only way you're going to be tolerated as a human interactor is if you help the robot reach sub-goals that are better than some other actions. So there's a combination of reinforcement learning and human interaction, and the human interaction is treated like an action that gets a high reward because it reaches a certain sub-goal. The other thing he discussed, which I thought was really, really interesting, was proprioception. Proprioception, which is sort of the idea that you have the positioning of your limbs and the sort of tension in your tendons and muscles and all those things. All of this is information that we humans signal, that our body signals to the brain, and we can have similar types of information for the robot. And what they're doing here is they're letting the robot, let's say, walk on ice or on very slippery surfaces, and the robot learns how to act on this without any vision. So the robot just learns how to act on this based on the proprioception, right? So think of it like you're blind, you're just touching and you're feeling and this and that, and then you then have also the vision, and then they're pairing this, so the vision and the proprioception, and they're creating a model where the robot literally sees something and already has a sense for how to behave based on vision. This is the idea. I find that incredibly powerful. It's something that I thought to myself also when I looked at the presentation by the gentleman from Aurora, also attended this week. I'm going to talk about it later, but he was presenting the sort of vision technology that Aurora is using, and my partner Zovina attended that lecture too. She asked herself, why do they need such good quality? And my answer was maybe because they can learn from the vision also about the surface of the floor and things like that. So this is definitely an interesting avenue. Agrawal is talking about how they're using tactile perception, so touch and things like that. They actually have mechanical engineers, fluid mechanics. They're using all these types of ideas within their lab to sense the touch. Like, for example, if a robot grasps something, they also want to be able to sense the touch. So this is, in my opinion, really interesting and worth pursuing. The paper Learning to See Physical Properties with Active Sensing Motor Policies introduces this, and I think, again, it's a really interesting concept. Next on the list, Shirin Sedibidokti, I might be butchering her name, University of Pennsylvania. Her talk was about neural data compression, learn how to compress data in data-driven approach. So there's a lot of data here. Now, in what she's trying to do is, she's a signal processing person. So this is hardcore electrical engineering, how to compress a signal. And there's been a lot of work done in terms of signal processing, and there's the JPEG and the MPEG and all of that stuff. And what is coming up now is neural data compression. So this is very similar to diffusion models, where you have noise, you learn how to denoise a picture to recreate a picture.
Now, in this case, you use diffusion the other way around. You take a picture, you reduce it to some theoretical level, and which is part of the talk, actually. How much can you reduce it? and then you reconstruct it, and you learn that through parametrization of a function, of a transformation function. So think of it like picture, transform, retransform. So this is, it's really interesting if you think about it, that, data compression is actually machine learning. It's the predecessor of machine learning. And information theory really is, the word says it, it's a theory about information. So what is machine learning? It's information. You're trying to assess information from data. That's what machine learning is. So I think this call really opened my eyes to what machine learning actually is. It's information theory. It goes way back. It's basic signal processing, signal to noise, those types of problems that are now, of course, amplified because we have a lot more applications than just transmitting data. What Shirin is talking about is data transmission, right? But you can also look at it the other way around. What can we learn from data? If we transmit a piece of information from A to B and we solve the problem of how can we compress that piece of information, well, we might as well learn from that piece of information and do something else with it, maybe inference and so on and so forth. Of course, machine learning is a lot more than just machines and learning, but this particular talk absolutely opened my eyes to the idea that these things didn't come from nowhere. These things didn't just happen out of nowhere. There is a body of literature, a body of knowledge that goes back to, in this case, signal processing, all the math, which is important. Shirin was talking about the theoretical limits of signal processing, which was really interesting. So this was the first part of the talk, in a sense. Okay, we want to sort of diffuse a piece of information and then reconstruct it. This is classic compression theory, but we're using neural nets instead of JPEG or other deterministic formulas. The other part of the talk I think was super, super interesting. Can we use text to compress pictures? So if I have a picture of, President Biden sitting in an airplane, right? It's Air Force One, right? Could I just put it in text? President Biden sitting in Air Force One drinking coffee, and then reconstruct it. Now, that is, of course, a pretty dangerous endeavor, in a sense that you're not going to get the kind of precision that a picture has. This goes to the fundamental question: can words say more than pictures? Can pictures say more than words? And sometimes words can say a lot more than pictures, and sometimes pictures can say a lot more than words. So this is philosophical at this point. But in terms of information processing and signal processing, we could say that in many cases, maybe it's enough. Look, President Biden sitting in an airplane. President Biden just landed in Shanghai. Like that's all I need to know. I don't care about the color of the leaves behind the plane and so on and so forth. You see where this is going. And I thought this was really interesting because at the Tesla AI Day, they kind of spoke about something along those lines, right? They said that we're putting traffic planning into a large language model, and then we're looking at it that way. And that, I think, caused quite a stir in the community ever since, if I look at the literature, archives full of papers that use large language models in robotics. So this is not new. But what I think is new here is the idea that you could potentially compress a lot of what the robot sees into language, use it as semantic guidance for planning, and go from there. Because you don't need the precision. Pictures can say a lot when they matter. Pictures often don't matter in the sense that it just doesn't matter what the color of the leaves is, right? Again, some people might say it does. And if we go back to the presentation from the Aurora person this week, who comes from the movie industry and tries to be incredibly precise and have high quality renderings, if we come from that perspective, then we, of course, are completely in a different regime. Then we're saying, no, in fact, pictures are all we need because we want to understand exactly what's in front of us, and we want to be able to maybe sense also is there ice and so on and so forth. But again, we could actually do that much more simpler by just telling the model, hey, there's ice there. So again, this is unbelievably interesting. I'm very intrigued. I'm very happy I attended this call. It was a Zoom call, which is unusual for me, but I kind of sense that this is more important than me just dismissing it. So I did it, and I was very happy. And thanks to Shirin for this call. Next on the list, Priyanka Raina. Now, this was really unbelievably important. So she is a hardware person, and she gave a talk about flexible hardware design. So the problem is the following. We have all these applications coming up, convolutional neural nets, LLMs, and who knows what's next. And these applications usually run much faster than the hardware. And the hardware gets developed. We have these, dedicated designs such as, Dojo at Tesla. We have TPUs at Google. And what she's saying is that very often these types of accelerators, as they're called, they lag behind, the software lags behind. And the fundamental problem is memory and compilers. Now, I don't want to go too much into the weeds because I don't know, but this definitely hits Onur Mutlu's problems also, which is in general, when we write these accelerators, there is the concept of push memory comes into play. So the way I understand it is that in traditional CPU, GPU type networks, you have requests for data. So the way it works is that the ALU, the arithmetic unit, the ALU, where the math happens, fetches a data that is necessary to complete a task. And in push memory, that's what accelerators do. In essence, they push memory to the logic units, or they even use some logic before they even push the memory to another logic unit. So it's more, that's why it's an accelerator, because it kind of knows what data needs to be processed at what point. Now, there's, of course, hybrids here in a sense that some of it maybe can be done like with GPU and CUDA, and that's exactly what CUDA does. And according to Priyanka, the big advantage of NVIDIA is really CUDA. We knew that already, but she just reiterated that, which was really interesting coming from a scientific background, that really cemented the thesis that NVIDIA has this advantage because it's using software to manage the data flow within their GPU clusters, which is really what Jensen Huang's always saying is that the data center is the unit of compute. Yeah, let's get back to Raina. Now, she's trying to flexibilize, I don't know if that's a word, but she's trying to make hardware design more flexible by having sort of a course something, I forgot the exact word, doesn't matter, some sort of abstract layer on top of the instruction set architecture where you can sort of have like tiles that you can rearrange. And for example, if you need to have a specific matrix multiplication hard-coded in the instruction set, you can do that. And then most importantly, you have a compiler that is already pre-designed to take advantage or to take into account these types of changes, so you don't have to rewrite the compiler. So this is kind of really, again, very high level. But let's say fundamentally what Priyanka was saying here is, again, we need some flexibility in hardware design without having to rewrite the compiler, in particular, the memory management system, which is where the bottleneck is today. That's what she said. This is a takeaway that I can take straight to Tesla, straight to NVIDIA, and ask the question, okay, how does Dojo work when it comes to memory management and compiler? You have to rewrite everything. And I think part of the reason why the Tesla technology, for example, Dojo and also the inference chip, maybe are a bit lagging behind its potential is because the software is lagging. Now, I'm not sure about that particular case with Tesla, but Priyanka said, if you don't believe me, just go and ask the TPU team at Google or go ask the team at Amazon. The accelerators that were developed, the hardware has been developed, but the software lags behind. And she kept reiterating the biggest advantage of NVIDIA is the software. And she said every time NVIDIA comes up with new features for their next generation of GPUs, the software team has to literally hard code all the specifics in the compiler. So it's all about the compiler. Well, what is the compiler? The compiler leads to high level programs into machine language. So that translation is the bottleneck. And you can flexibilize this. Mark Horowitz is the professor at Stanford who is part of that group, and I don't know if he works with Priyanka or she works for him or with him, doesn't matter. But he co-wrote a paper about this that I will put in the show notes. Here is some excerpt from the paper. I really think this is super important, and it touches upon what Onur Mutlu is writing. And here's the quotes from the paper. So, a coarse-grained reconfigurable architecture (CGRA) is a reconfigurable architecture that operates on coarser granularity than traditional reconfigurable architectures such as FPGA. It contains an array of tiles where each tile is either a processing element, PE, or memory tile. Our PE tiles perform arithmetic on 1-bit and 16-bit signals, while memory tiles store and push data. The tiles communicate through configurable interconnect. So what does this mean? We have tiles. I remember Tesla talking about tiles. I'm not sure if it's the same thing. I believe this is the same idea. And these tiles are reconfigurable. You have logic tiles, you have memory tiles, and you can kind of put them together like Lego stones. And you don't have to rewrite the compiler every time you change something in the hardware. And again, the fundamental idea is to go with the applications to be faster. If we have convolutional neural nets today, tomorrow we have LLMs. Next thing we have LLMs combined with, let's say, what the researcher from MIT is doing, where he's combining large language models with sort of low-level data. Shirin Song's doing that. So we have this combination of different types of models using. So hardware needs to go with that flow, and that's what Raina and Mark Horowitz are doing in her lab. So in their labs, excuse me. So to summarize the first 4 talks that I presented from last week, number 1, Shirin Song, she talks about the need for better data, robot complete data, and those sort of things. The researcher from MIT that talked about dextrous hand manipulation, the necessity to do tactile sensing, the idea to combine sensing of the robot while the robot is balancing on ice with vision, and then use that as a sort of multimodal approach towards robotics. We had Raina talking about flexible hardware design, this coarse-grained architecture, which I think is really interesting, dealing with memory and compilers. And lastly, the paper about signal processing and using diffusion models for signal processing, and how machine learning and diffusion and signal processing really are all one problem, just looking from a different perspective. Thank you.